Yeah.
In our first demo, we did the law of conservation of energy, which is PE plus KE equals PE2 plus KE2, which then becomes MGH plus 1 half MV squared equals MGH2 plus 1 half MV2 squared. And then since you don't change mass during the trip on the swing, you can cancel out the masses, so it becomes GH plus 1 half V2 squared equals GH2 plus 1 half V2 squared. Now, on the pendulum, you notice that I marked 1, these two both 1 since they're both going to be the same height, and then this is 0.2. At 0.2, the velocity in the x direction will be the highest, and its y position will be the lowest. And then at its highest y position, the velocity will be in the x direction will be 0 since you're turning around, and that causes you to have 0 velocity momentarily. So I just rewrote the equation PE plus KE equals PE2 plus KE2, and then I substituted in I rewrote the formula with its units, and then I canceled out the masses, and then I substituted in the value, so it's 9.8 meters per second squared plus 3.804 meters plus 1 half, times 3.804 meters plus 1 half 0 meters per second squared equals 9.8 meters per second squared times 2.381 meters plus 1 half V2 squared. So 37. So then I did that and I calculated and got 37.28 meters squared per second squared equals 23.3 meters squared per second squared plus 1 half V2 squared. And then I did 13.95 meters per second squared per second squared equals 1 half V2 squared. I got that by subtracting the 37.28 by 23.33 meters per second squared, and then 27.9 meters squared per second squared equals V2 squared. And then I squared rooted both sides and got V2 equals 5.28 meters per second. If you look on the graph right here, you notice that at its lowest point, 2.381, it's at 5.313 meters per second squared. Meters per second, excuse me. The reason it's different is because when I was doing the things, I wasn't able to mark the same exact spot every time, which caused the difference in the velocity. But they're both really close.
Yeah.
Ready?
Ready?
Yep.
All good?
Yeah. So for our second demo, we did whether mass affects how fast you get on a slide. So using the conservation of energy, mass has no effect on how fast you end up coming off a slide as your final velocity, as long as you both use the same starting force. And here is the reason why. So you do all this to get the formula, and then 9.8 meters per second squared times 10 meters high, as our example, plus 1 half 0 meters per second, since you're starting at rest, squared, equals 9.8 meters per second squared times 0 meters, since that's what our ending height, plus 1 half V2 squared. And then you do 98, so then you get 98 meters squared per second squared equals 1 half V2 squared. Then you times 98 by 2 and get 196 meters squared per second squared equals V2 squared. And then you square root both sides, and then you get V2 squared equals 14 meters per second. Sorry about the typo. I messed up. But yeah, so you could have a baby or an adult do this, and they'll both go down the same speed as long as they both use the same starting force. Okay, go.
Football, 0 degrees.
30. Yeah.
30 degrees. Oh. Ready?
Yep.
45.
Okay, I'm ready.
60.
Okay, ready.
90.
For our third demo, we did projectile motion, and we wanted to show that in the absence of air resistance, 45 degrees will get the ball the farthest. So the resultant is equals the radical of cx squared plus cy squared, which is the components of x and y. And then to find the components of x and y, you have to do cx equals resultant cosine theta, and then cy equals resultant cosine theta. So then let's say c equals 25, and we were to put for 45 degrees, as theta equals 45 degrees. So it would be 25 cosine 45 and then 25 sine 45, which you get 17.7 as both of the components. And since they're both going to be the same, it's going to go up and travel as far as it can, making it go the farthest in the absence of air resistance.